Hi, I'm Marissa Dubois, a senior graphics engineer with Intel. Welcome to my talk, The Evolution of Variable Rate Shading in Games. There are a few topics I'd like to cover with today's agenda. First, I'll talk about the history of games and engines we have enabled with variable rate shading. Second, I'll deep dive into how we enabled our velocity and luminance adaptive rasterization technique in World of Warcraft. After, I'll talk about the future of VRS and some ideas for combining it with XeSS. And then finally, I'll discuss how to improve visual quality when using Valar with XeSS. In 2019, Intel introduced our 10th generation processor graphics codenamed Ice Lake. Ice Lake was the first Intel GPU to support variable rate shading Tier 1 through the use of the RSset shading rate API in DirectX 12. In 2022, Intel released our first mainstream discrete GPU codenamed Alchemist. The A-series GPUs were the first GPUs by Intel to support VRS Tier 2. VRS Tier 2 supports image-based and per-primitive VRS using the RSset shading rate image API. Over the last few years, we have been working with our ISV partners to enable variable rate shading support in a variety of games. We have several games that now support VRS Tier 1, which include World of Warcraft Shadowlands, Monster Hunter Rise, and Farming Simulator. Each game applied VRS Tier 1 in a slightly different way. WoW used VRS Tier 1 on their terrain tiles. Monster Hunter Rise uses a pre-pass approach to reduce the cost of render passes. And FarmSim 2020 applied VRS Tier 1 to their particle systems. Next, we have games that support VRS Tier 1 and Tier 2. Hitman uses both Tier 1 and Tier 2, and they have implemented a Luminance-based mask for VRS Tier 2. World of Warcraft Dragonflight supports the original VRS Tier 1 from World of Warcraft Shadowlands, but now has added support for Intel's velocity and luminance adaptive rasterization algorithm. Finally, we have added support to Unreal Engine 4.26 for VRS Tier 1, which we call Per Material. Chivalry 2 was the first game to support VRS Tier 1 in Unreal Engine. They've implemented 3 different modes, including Relax Mode Plus, Per Pass, and Per Material, which was used as a workaround for visual issues. And recently, Dolmen took advantage of the VRS Tier 1 Per Material system using the built-in LOD system for Unreal Engine. In addition to launching several games that support variable rate shading, we have produced several white papers and videos demonstrating VRS Tier 1 and Tier 2 for developers. If you want to learn more about the background for this presentation, please refer to the links below. Now I'd like to discuss our VRS Tier 2 algorithm, known as Velocity and Luminance Adaptive Rasterization, or Valar for short. We originally disclosed Valar with a white paper and a GDC demo in 2022. Our algorithm is based on a paper called Adaptive Shading by Li Yang, which was published in 2019. Valar approximates a perceptually lossless output using Weber-Fechner contrast laws. It does this by computing the mean squared error of luminance and compares it to a just noticeable difference threshold. I'll go into more detail on the mean squared error and just noticeable difference threshold in the next few slides. There are several adjustable input parameters used to control Valar, primarily the sensitivity threshold T, the additive environment luminance E, and the quarter rate shading modifier K. You can refer to our white paper that we published in 2022 to learn more about Valar. In order to implement Valar in a rendering pipeline, we need to make a few minor changes to the renderer to implement the feature. First, Valar requires a color buffer and an optional motion vector buffer. In order to implement Valar in a rendering pipeline, we needed to make a few minor changes to the renderer to implement the feature. First, Valar requires a color buffer and an optional motion vector buffer. Second, we added a call to set shading rate image after rendering the velocity buffer, but before rendering the color buffer. Once the color buffer is rendered using the Valar image mask from the previous frame, we then compute a new mask to be used in the next frame. The first frame will always be rendered without a mask, but each subsequent frame after will always have a Valar mask applied. To generate the mask, we need to compute the tile-based luminance that will be used later on to compute the mean squared error. First, we convert RGB values into luminance values by using a luminance conversion equation on each pixel. Then, we sum the luminance for each pixel in the 8x8 or 16x16 VRS tile. Finally, the luminance sum is averaged by dividing the total number of pixels in the tile. Next, the mean squared error of the average tile luminance is computed. First, we sum the luminance delta for both the x and y axis of the tile. This is an example of the equations for approximate mode, but it is also possible to use what we call a Weber-Fechner mode to control precision in some cases. After the differences are summed, we can compute the average change in luma for each axis using the equation shown. And then finally, using a square root on the average x and y delta, we arrive at the mean squared error values for x and y, shown here as epsilon sub x and epsilon sub y. The final values are then compared to the just noticeable difference outlined in the next slide. Once the mean squared error has been computed, we can compute the just noticeable difference value for the tile. We derive the J and D threshold J by multiplying the average tile luminance L sub T plus an additive environment luminance value E by the sensitivity threshold. The T and E terms are both user configurable values. I'll describe how these controls work in the final section of this talk. After calculating the just noticeable difference threshold, it is then compared to the mean squared error for both the x and y axis of the tile. This can be done using a branchless expression, which is essentially logic embedded in a mathematical equation. Each logical term will either evaluate to 0 or 1, which is then multiplied by the half or quarter rate shading constants, r sub 2 and r sub 4. These terms should be mutually exclusive in order to produce a 2x or 4x shading rate. However, both terms can evaluate to 0, which would result in a 1x shading rate. Branchless expressions can be a useful trick to reduce branch code by relying on the ALU or FPU instead of masking off threads with divergent branches on the GPU. We can then use a bit shift operation to combine the x and y shading rates into a single shading rate for the tile. Additionally, we can introduce optional motion vectors to modify shading rates based on velocity as well as luminance. First, we get the minimum velocity for each VRS tile. We can then use the velocity curve equations provided by Li Yang in the adaptive shading paper from 2019 to compute the half and quarter rate velocity modifiers. These exponentiated equations can be substituted with a linear approximation. And finally, the branchless just noticeable difference equation from the previous slide can be modified by the half rate and quarter rate shading modifiers. Using motion vectors can cause the sensitivity of the algorithm to increase while under motion. However, by using the Weber-Fechner contrast laws, the quality loss is obscured by motion and motion blur. You can also pre-compute repeated expressions to reduce computation. Next up, I want to take a deep dive into the work we've done with World of Warcraft Dragonflight, along with the team at Blizzard to implement our Valar algorithm. We integrated Valar with two modes in World of Warcraft Dragonflight, Standard and Aggressive. Standard is intended to be minimally perceptible to the user, while Aggressive is intended to be just within the range of user perception. We selected out NPCs and player models to always render with a 1x1 shading rate, while opaque geometry and doodads are rendered with a screen space shading rate. For Standard, we chose a sensitivity threshold of 0.31, and for Aggressive, we chose a sensitivity threshold of 0.5. We selected a quarter rate shading modifier of 2.13 as derived in the Li Yang adaptive shading paper from 2019. We also disabled motion vector mode and used approximate mode instead of the more precise Weber-Fechner mode. There are a few things we needed to consider to get our integration to work. World of Warcraft uses multiple command lists, which each need VRS masks applied. World of Warcraft does not support motion vectors in their renderer, so we couldn't use motion vector support in Valar. And over the course of the integration, we discovered a visual corruption issue with shaders that used a manual alpha test with discards. And I'll go into more detail about how we resolved that coming up. This is an example of the World of Warcraft command list architecture with Valar integrated. In several of these command lists, we are setting and unsetting the VRS Tier 1 image mask. On the default command list, we subselected doodads to render at the screen space shading rate, while all other draw calls render at 1 by 1. For the no reflection opaque command list, we didn't set a VRS Tier 2 mask to allow NPCs and players to render at 1 by 1. And then finally, each other command list was rendered with the Valar mask applied. Given our past experience developing games with VRS, we anticipated that there might be visual issues introduced with a naive integration. Once the Valar shader was added and tested, it became apparent that manually alpha-tested geometry was causing a visual corruption when interacting with variable rate shading. We narrowed it down to a specific set of observations. It exhibited black pixels, typically on the edges of foliage. It did affect some models and buildings, and we isolated this to shaders using a manual alpha test, which used a discard. We brainstormed several approaches to resolve the issue. First, we considered adding additional command lists, but this would require large architectural changes to the engine. Second, we looked at modifying the manual alpha test shaders to compute fine pixel offsets. We had a prototype that fixed the majority of the corruption, but without a major rewrite of shaders, this was going to take too much time to resolve. So finally, we determined that we could strategically use variable rate shading combiners to subselect the manual alpha test geometry out of the Valar mask. To set our new combiner, we only had to make relatively minor changes to the model and building command list to swap combiners. By default, Valar uses a pass-through and override combiner to allow the VRS mask to override the shading rate of each draw call. Just before drawing manual alpha-tested geometry, we added a pass-through combiner, and just after calling a manual alpha-tested draw call, we reset the combiner back to a pass-through override combiner. So what are combiners exactly and how are they used? Combiners are part of the DirectX 12 API and are used exclusively to control shading rates for variable rate shading. They can be applied in 4 different ways, though one of them is somewhat overloaded. Combiners can control shading rates from pixel shaders, vertex shaders, geometry shaders, and in image-based through compute or CPU. There are only 2 combiner slots, however, combiner 1 is doing double duty on per provoking vertex and per primitive shading rates. We use per draw and image-based combiners in World of Warcraft. There are several types of combiners, each of which give a different behavior when combining shading rates. As mentioned, we use both pass-through and override combiners in World of Warcraft. However, there are also min-max and sum combiners. Min and max pick the lowest and highest shading rates respectively, while the sum combiner can add 2 shading rates. For example, a 2x shading rate plus a 2x shading rate is a 4x shading rate. However, for the sum combiner, it's only supported on some GPUs, so you'll want to check your hardware specifications. There is a straightforward API using RSSet shading rate to pass in a base shading rate and 2 combiners in an array. Like I mentioned before, we use 2 combiners in World of Warcraft. The default combiner to support screen space shading rates was the pass-through override combiner. This works by first allowing the per draw shading rate to pass through combiner slot 1. Using override in combiner slot 2 lets the image-based shading rate take precedence. In the example given, a 4x4 screen space shading rate would override a 1x1 per draw shading rate. The second combiner is the manual alpha test pass-through combiner. This one works by allowing the per draw shading rate to pass through combiner slot 1 and 2. In the example given, the per draw 1x1 shading rate takes precedence over the per primitive and image-based shading rates. Here's an example of an area in World of Warcraft Dragonflight, which was rendered in 4K with quality level 5. In this example, Valar is disabled. Now here's the same area rendered in 4K, quality level 5 with Valar set to standard. Again, the sensitivity threshold here is 0.31. The quarter rate shading modifier is 2.13, and the environment luma is 0.05. Hopefully you'll have a hard time noticing any visual differences over the previous image. Standard mode was designed to introduce minimally noticeable visible changes. Here's the same area again, also rendered in 4K with quality level 5, but this time we're using aggressive mode for Valar. For aggressive mode, the sensitivity threshold is 0.5 and the quarter rate shading modifier is 2.13, while the environment luminance stays at 0.05. Aggressive mode was designed to introduce more noticeable visual changes, but should still produce a reasonable quality when compared to the control image. Here's a side-by-side comparison from the previous image. It can be observed that as the sensitivity threshold of Valar increases, it will introduce more aliasing to the final image. However, the algorithm is still designed to produce the least noticeable change for a given scene. One thing to point out here is that we use the pass-through combiner to preserve the fidelity of the foliage. Zooming in on a different part of the arch from the earlier screenshots, we can observe the change in visual quality and aliasing as the sensitivity threshold increases. As mentioned earlier, the visual quality difference for Valar standard is intended to be minimally perceptible, while aggressive will have a slightly more noticeable visual quality difference. Okay, now we'll talk about the performance uplift for both standard and aggressive modes. This test was run on a 20-core i7 CPU with both a A370M and an A380 ARC series discrete GPU. These GPUs are typically rated for 1080p rendering. However, by implementing our optimizations, we were able to push the envelope and have this game playable at 4K with quality level 7, which we then tested in the Vol'dun area of World of Warcraft. As you can observe, the A370M had an uplift of 1.15x for standard and 1.16x for aggressive, while the A380 had an uplift of 1.10x for standard and 1.11x for aggressive. The uplift for aggressive is only marginally higher, likely due to the bottleneck being alleviated with a less aggressive sensitivity. Now that we've proven the viability of our technique in production software, I'd like to shift gears a bit and talk about how I think Valar could be used in the future alongside emerging supersampling techniques like Intel's XeSS. Supersampling, or XeSS for short, is a machine learning-based supersampling technique which produces a temporally stable anti-aliased output. It supports both low-res and high-res motion vectors, and there are 4 common scaling factors: ultra, quality, balanced, and performance. As we discussed earlier, Valar is our VRS Tier 2 subsampling technique, which approximates a perceptually lossless image output. Valar also supports low-res and high-res motion vectors, and the performance of the Valar compute shader is relative to the input resolution. We needed to take a few considerations into account when doing the integration. First, we need to be able to translate between input and upscaled coordinate systems. We also needed to add support to Valar for high-res motion vectors, and in the next section, we'll discuss ways to improve visual quality when using them together. Integrating Valar and XeSS is pretty straightforward. Just as before, we pass the input resolution velocity and input resolution color buffer into the Valar compute shader. Then, after we compute the Valar mask, the input resolution velocity and input resolution color buffer is then passed to the XeSS upscaler. And this is the section of the pipeline that we had to modify to add support. Now I want to talk about the relationship between VRS tile sizes and scaled resolutions. VRS tile sizes are defined by the GPU hardware. For Intel, our tile size is 8, but for other vendors, the tile size may be 16. You'll want to make sure you query the DirectX 12 hardware features to see which tile size your hardware supports. The number of VRS tiles is relative to the input resolution. You can compute the number of input tiles by dividing the input width by the tile size and multiplying it by the input height divided by the tile size. There are 2 examples here for 2K and 4K input resolutions. 2K results in 57,600 tiles, while 4K results in 96,000 tiles. The common scaling factors for XeSS are 1.3 for Ultra, 1.5 for Quality, 1.7 for Balanced, and 2.0 for Performance. We can prove that input and upscaled tile sizes are not equal with the following equations. To calculate the number of pixels for the input resolution, we just square the GPU tile size. But then in order to calculate the number of pixels for the upscaled resolution, we multiply the tile size by the scaling factor and then square the result. We can then use a simple greater than or equals equivalence to show that the upscaled tile size is greater than or equal to the input tile size. For example, we can compute the number of input resolution pixels per tile with the T sub I equals T squared equation, which results in 64 pixels for an 8x8 tile size and 256 for a 16x16 tile size. Finally, the number of upscaled pixels per tile is computed for each scaling factor with the T sub U equals S times T squared equation. For Ultra, there are approximately 108 pixels per tile. Quality is about 144 pixels per tile. Balanced is about 185 pixels per tile. And Performance is 256 pixels per tile, which is actually similar to the 16x16 tile size. Now I want to talk about pixel coordinate conversions. Starting from the upscaled render target, we need to translate to the input render target. We can translate from the upscaled pixel coordinate P sub U to input pixel coordinate P sub I. We can then translate from the input pixel coordinate P sub I back to the upscaled pixel coordinate P sub U. But then next, we'll need to translate to the shading rate buffer. And in order to do this, we can convert the input pixel coordinate P sub I to the shading rate tile P sub R. So in order to do these pixel coordinate conversions, we can employ the following equations. First, we can compute the scaling ratio where the scaling factor S equals the input resolution I divided by the upscaled resolution U. The values represented here are 2D vectors. Next, we can compute the input pixel coordinate P sub I by multiplying the scaling factor by the upscaled pixel coordinate P sub U. Once the input pixel coordinate is computed, the pixel coordinate for the shading rate tile is computed as P sub R equals P sub I divided by T, where T is the hardware tile size. Now we can convert from the input pixel coordinate back to the upscaled pixel coordinate using the equation P sub U equals P sub I divided by the scaling factor S. However, P sub U is within a set of pixels from P sub U to P sub U plus the tile size minus 1. As an example, if we have a 1D array of upscaled pixels, input pixels, and shading rate tiles, we can convert with the equations described. Going from the upscaled resolution to input resolution, we use P sub I equals scaling factor S times P sub U. And then to convert from input resolution to the VRS tile, we use the P sub R equals P sub I divided by T equation. Both Valar and XeSS support low-res and high-res motion vectors. Input resolution and motion vector resolution are equal. Low-resolution motion vectors work out of the box with Valar, and in some cases, jittered motion vectors can help improve image stability, but this is going to depend on your engine and your art. And then for high-resolution motion vectors, the output resolution and motion vector resolution are equal. High-resolution motion vector support was added to Valar, and again, in this case, jittered motion vectors can help, but you'll want to do a visual quality assessment to make sure you're not introducing other visual quality issues. Using the equations from the previous slide, we can convert between coordinate systems to select the correct motion vector. With low-res motion vectors, there is one motion vector to many output pixels, and there is a one-to-one correspondence between motion vectors and input pixels. We use the P sub I equals S times P sub U equation to convert from the upscaled pixel coordinate to the motion vector. With high-resolution motion vectors, there are many motion vectors to one input pixel. You can use a sampling pattern or a min-max, median, or average approach to compute the value for your algorithms. And you can use the P sub U equals P sub I divided by S to convert from an input pixel to a high-res motion vector. Using XeSS and Valar together can yield a significant reduction in pixel shader invocations. For our experimental setup, we tested each XeSS scaling factor alongside each Valar mode to compute the relative reduction in pixel shader invocations. These experimental cases are compared against the control of the XeSS mode plus Valar off. We used 3 sensitivity thresholds for Valar, which are quality at 0.25, balanced at 0.5, and performance at 0.75. Using this experimental apparatus, we can observe the following results. Pixel shader invocations are always relative to Valar sensitivity. Valar quality mode results in an approximately 1 to 2% pixel shader invocation reduction, while Valar balance results in approximately a 15 to 20% reduction. And finally, Valar performance results are approximately 30 to 35% reduction. These reductions are consistent across all XeSS scaling factors. Once XeSS and Valar are both integrated in a game, it's important to conduct a visual quality assessment and then fine-tune the quality settings to meet the art standards for your game. There are a few strategies to consider to improve visual quality. Typical visual quality issues are usually aliasing, moire, flicker, or corruption. Each of these issues may require a different method for resolving. The first method is to fine-tune the parameters for Valar or to use a more precise shading mode or dynamic shading rate technique. Next, you can fine-tune the parameters for XeSS by selecting a quality mode, adjusting MIP bias, modifying the sharpening, or using jittered motion vectors. And then finally, we can also use an API quality tuning strategy in some cases by using VRS combiners or multiple command lists. For example, you may employ a range of techniques to reduce aliasing, which may involve one or all 3 of these approaches. For moire, you may need to tune your XeSS quality settings. Again, with flicker, there are multiple approaches that you can take. You can try to use one or all of these techniques combined. And then finally, for corruption, these are usually best resolved by using an API quality tuning method, such as VRS combiners or multiple command lists. The Valar algorithm can be fine-tuned using several controllable parameters. The primary parameter to tune Valar is the sensitivity threshold. It controls the just noticeable difference sensitivity. The sensitivity threshold is a floating point value in the range of 0 to 1. You could consider segmenting these values into discrete settings such as quality at 0.25, balanced at 0.5, and performance at 0.75. Values closer to 0 produce images closer to ground truth but execute more pixel shader invocations, while values closer to 1 produce images with more aliasing but fewer pixel shader invocations. The second parameter in the just noticeable difference equation is the additive environment luminance value. Environment luminance is a positive floating point value which is unbounded. Because it is additive, environment luminance can significantly increase the just noticeable difference sensitivity as values get larger. Values closer to 0 produce less aliasing, while larger values produce more aliasing. Consider using environment luminance in low light conditions or have it tied to your global illumination system. Next, we have the quarter rate shading modifier, which controls the 2x4, 4x2, and 4x4 shading rates. It's part of the luminance and velocity mean squared error equations and not the just noticeable difference. Like environment luminance, it is a positive floating point value that is unbounded. However, unlike environment luminance, values closer to 0 produce more 4x tiles, and larger values produce fewer. Lower values means fewer pixel shader invocations but more aliasing, while higher values produce more pixel shader invocations and less aliasing. In addition to the tunable parameters, there are also a few modes that can help control the behavior of Valar. The first is the 2x2 only mode. 2x2 only mode disables 2x4, 4x2, and 4x4 shading rates, but increases the number of 2x2 tiles. This can help reduce aliasing or flickering in the final image. Additionally, there's a mode called Weber-Fechner mode. This mode can help improve the precision of the mean squared error algorithm. By default, we use an approximation in the mean squared error, but using Weber-Fechner mode gives us more direct control of precision. It does this by reading neighboring luminance values and has a controllable parameter known as C, which is a positive floating point value that starts at 0 but is also unbounded. Values closer to 0 are more conservative about tile placement, while larger values produce more aggressive tile placement. Even as the tile placement becomes more aggressive, the Weber-Fechner mode still strives to preserve as much visual fidelity as possible. You can also consider adding a dynamic threshold to automatically enable or disable Valar at runtime or auto-adjust the sensitivity threshold. For example, you can turn Valar on when you are GPU bound by using a simple comparison to test if the average GPU time is greater than or equal to the average CPU time within a margin of error of about 5%. The sensitivity threshold can be controllable with a target FPS. You can divide the average GPU time by a target FPS, which is converted to milliseconds by multiplying it by 1,000. Similar to the dynamic threshold from the prior slide, you can also control sensitivity or shading rates using a camera or player controller. First, we have what is known as relaxed mode, where we can compare the previous camera position to the current camera position to disable Valar when there is no movement and then to enable it when the camera does move. We've also demonstrated what we call Relaxed Mode Plus with VRS Tier 1, where we can apply a uniform shading rate based on the direction of movement of the camera or player controller. When the camera moves left or right, we can set a 2x shading rate for the x-axis, and when the camera moves up or down, we can set a 2x shading rate for the y-axis. When there is a combination of movement in both up and down and left and right, we can set a uniform 2x2 shading rate. This technique was shipped in Chivalry 2 by Tripwire, which was released in 2021. We did this by using the camera controller to swap Tier 1 shading rates when yaw and pitch change, or when the player moves forward and backward or left and right, we can also swap the Tier 1 shading rates. And finally, when the player sprints, we can just set a uniform 2x2 shading rate. In this way, we can obscure aliasing by using motion and motion blur, which helps trick the human visual system to see less aliasing when in motion. In addition to parameter tuning Valar, there are also several parameters that can be used to control the behavior of XeSS. First are the quality modes, which we have referred to as a scaling factor in earlier slides. The scaling factor has a significant impact on the quality of the final output image. Lower scaling factors also decrease VRS coverage, while higher scaling factors give more precise VRS coverage. In the example on the right, we show that with the XeSS Ultra, we have the most precise coverage with about 18 by 15 VRS tiles and a total of about 64 shaded tiles in the example image. As we move down to lower scaling values, we reduce to about 12 by 10 tiles with approximately 13 shaded VRS tiles with XeSS performance mode. We can also control sharpening with XeSS parameters. Sharpening is another floating point value in the range of 0 to 1. Values closer to 0 produce a less aliased but blurrier output image, while values closer to 1 will produce a more aliased but sharper image. MIP bias can also be used to adjust the output image quality by selectively biasing the MIP level. MIP bias is an unbounded floating point value that can be negative or positive. Negative MIP bias will produce an output image with increased contrast but less VRS coverage, and a positive MIP bias will produce an output image with less contrast, which increases VRS coverage. Be aware that adjusting the MIP bias can cause flickering, and in most cases you should choose the recommended settings from the XeSS developer guide. You can try to use jittered motion vectors to help reduce flickering with MIP bias, but this would require a visual quality analysis to prevent visual issues. In some cases, we can use the DirectX 12 API to control visual quality, and this can be done in two ways. First is by using the VRS combiners, which we've demonstrated in World of Warcraft. We can use the pass-through combiner to create hero assets or to reduce flickering and visual corruption. And then second, in a similar way, we can use multiple command lists to segment out hero assets, which can help reduce flickering from VRS or visual corruption. It's worth mentioning that each command list could have a different VRS mask for special cases. Okay, now I'd like to play a demo video from our mini engine example. In this example, we're using XeSS balanced plus Valar balanced to demonstrate visual quality differences between 2x2 only mode disabled and 2x2 only mode enabled. So as we zoom in, if you look in the top left corner, you can see that it has some aliasing and some flickering with 2x2 only mode disabled. However, for most geometry, we are able to preserve visual fidelity pretty well overall. As we come around here, we'll see some foliage that we've actually rendered with VRS, but we've been able to preserve a lot of fine detail due to the nature of the just noticeable difference algorithm. As we come around the corner here, we'll see a smoke particle system. This particle system is actually rendered with Valar, as you can see by this overlay. The pink on the image represents the 4x4 shading rate. And as we come back around, we'll see that that light that was rendered is covered in the pink tiles, which means it used a lot of 4x4 shading rate tiles to render. Okay, now we'll show you this again with 2x2 only mode. And as you can see in the upper left-hand corner, the light looks much sharper. We're still preserving a lot of the fine details, but we've fixed that one issue. Again, you'll notice that the image looks roughly the same as before. We're still preserving the visual fidelity and the fine detail, like the stonework and foliage. And then again, the smoke particle system is still going to be rendered with Valar, but this time you'll notice it becomes green to represent the 2x2 shading rate. We have a lot more 2x2 tiles with this mode. And then as we come back around, you'll see that this light is now rendered in mostly green tiles. I'd like to thank the following people who've helped with this project along the way. It's been several years in the making. I'd like to specifically give a shout out to the World of Warcraft engineering team at Blizzard. Without their support, we never would have been able to prove that this technology worked in a production software environment. And that wraps up my talk. Thanks for watching.